The second point, I want to talk about the conservative force. In general, FC. Here we have two conditions. In general, the work done by FC on any object is independent to the path. We can say, first of all, omega. Let's say here we have position 1 and position 2. We can pass from 1 to 2 through the path 1 or through the path 2. Okay? As the work is independent to the path, the work done through the path A from 1 to 2 equals to the work done through the path B from 1 to 2. If you have here also a path, let's say path C equals also omega through the path C from 1 to 2. This is the first point. The second point, let's take this figure. We can say omega through the path A from 1 to 2 equals to minus omega through the path B from 2 to 1. Omega from here to here equals to minus omega from 2 to 1. We can also say equals to minus omega through the same path from 2 to 1. So omega 1, 2 equals to minus omega 2, 1 from here or from here. These are the two conditions in order to have a conservative force. In general, we have many examples of the conservative force. The example. First of all, the gravity. mg is a conservative force. Fs, you know, in the case of a spring, if we have a spring and we push the object, here we have the equilibrium position. If we push the spring to the right, the spring will resist with Fs. And you know Hooke's law, Fs equals to minus Kx. This Fs is a conservative force. This is the second example. We can have also an example, the electric force Fe. So we have mg, Fs, and Fe are conservative. If you have another example of non-conservative force. Before, let me give you another properties of the conservative forces. The work done by any conservative force equals to minus delta potential energy. Okay? In the case of gravity, omega mg equals to minus delta potential energy, delta gravitational potential energy equal minus 2 mg y2 minus mg y1. Okay, this is 1 equal minus 2 potential energy gravitational final minus potential energy gravitational initial. Okay, this is with respect to mg. Also, if we take fs, in the case of fs, omega fs equals to the minus electric or elastic potential energy equals to minus elastic potential final minus elastic potential initial. And you know, the elastic potential energy equals to half kx square final minus half kx square initial. In general, just I want to tell you the work done by the conservative force equals to minus delta potential energy. The same in this chapter, I want to talk about the electric force and the calculation of Fe, and we see later that omega Fe equals to minus to the electric potential energy. We see this in this chapter. So here we saw two examples. Here, just a simple example of a non-conservative force. Here we have an object at this point. I want to push the object from the position 1 to the position 2. We have path 1 from here, and here we have path 2. You know, the work done by the friction equals to minus F times the distance. Here we have a long distance, and here we have a short distance. So in this case, the work done by F is or depends on the path. In this case, we cannot say the friction is a conservative force. It's a non-conservative force. So here just we talk about F electric, and we can say we can resume omega Fe equals to minus delta potential energy. And potential energy in general, you can write Pe or you can write U, okay, equals to minus the final potential energy minus the initial potential energy, U2 minus U1. We can say the potential energy can only be defined for conservative forces like the gravitational mg, like the elastic fs, like the electric fe, and the non-conservative like the friction, air resistance, tension in the cord, and so on. Now we are interested just about the electric force Fe. And in this case, we can say the change in the potential energy is defined to be the negative of the work done by the conservative force. We can say delta omega F conservative equals to minus delta potential energy.